Welcome everybody to my talk on mobile robotics and HRI in the fruit harvesting chain. I'm a bit of an alien, let's say, in this workshop, as I'm not going to mostly talk about tasking from grasping here, but I'm going to try to give you a bit of an overview of the entire harvesting chain and the related robotics applications and tasks that we may consider as well, going a little bit beyond grasping in its own right, if you think. So we're going to dive right in. And I want to give you a little bit of the challenges that you may well be aware of. So within the soft fruit production, there is a massive reliance on manual labor, because this is, as you will fully appreciate, it requires a lot of dexterity to actually pick fruits, and also in general to deal with these very flexible and very dynamic environments of farms here. And of course, I mean, being in the UK, we have the big B word, Brexit, where we actually see a lot of challenges these days to get the workforce to go out on our farms and actually harvest the crops. So there's a lot of drive behind this at the moment, because indeed there is crops rotting in the fields because they just cannot be harvested in time. So we see this kind of shrinking workforce, and this is due to particularly on the reliance of foreign labor coming into the country, and that not for political reasons being so welcome anymore. That there is a big push to actually go towards automation and using robotics in such domains. So that just to kind of set the scene, what we're looking at. The most of the work that I'm going to talk about is indeed as a sort of soft fruit production. You see this on the right hand side here, where we're growing strawberries on tabletops, and we can discuss a little bit about the picking operations that this requires as well. But all you can here see a glimpse of the sort of robot that we are utilizing, which is a so-called Thorvald platform by our collaboration partner Cycle Robotics, which they use and we also use in a variety of tasks and applications, which is what I'm going to talk about a bit more as we move forward. So I'm going to embed this into the context of a larger project, one of our biggest projects in the area of automating soft fruit production, which is called Robot Highways, and it's called multiple high TRL solutions demonstrated across an actual commercial farm. That's our ambition. So with in a year's time, we will show a number of robotic applications actually deployed in a commercial environment. And what I really wanted to highlight here, that we are facilitating this journey towards automation. So there may be tasks that we can already do pretty much now with the robotic technology that is available, and we will see that along this journey, moving along this line towards automation, also manipulation will come into the play. But it's not the only task that we're going to look at. So just to give you a quick run through what is the ambition of this project, which will be one of the largest scale demonstrators of robotics technology in a farm as an integrated system, is that as a first we're trying to solve the perception challenges. Perception is required both for the manipulation, so in order to detect and estimate where the fruits are, and also to assess their respective status, so that we know that these ones are ripe and we only pick the ripe ones. And it's not only about perceiving the individual fruits, as you can appreciate, we also need to model the environment, the surrounding of the fruit, in order to be able to do things like grasp planning in the presence of obstacles. So a lot of the work that our colleagues do, they also organizing this workshop, is to do actual manipulation planning in the context of having obstacles around that you need to work your way around and move into this. So that is the sort of perception challenge, and we've got people to work on that. Then we have the areas of crop care, so where you're actually not trying to harvest the crops, but you're delivering interventions to it in order to prevent it from getting seriously ill. And this is one of the areas that is already quite far advanced. So for instance, we have got our colleagues from Cycle Robotics who are already on a pre-commercial scale treating every night up to 10 hectares of strawberry farms, these kind of strawberries as you see them on tabletops, in an actual working environment with UVC light. And that UVC light is there to prevent the development of powdery mildew, which is one of the main reasons for rotting fruits. And so we're going to replace the need for any sort of fungicides, chemicals to battle this disease completely by just shining light on these crops during nighttime. Very closely related is the idea of autonomous spraying, and again, that is very far advanced because all it really requires is autonomous navigation at a constant speed, very much the same as for this sort of UVC treatment. Now, moving forward, this is probably the area that is mostly of interest to you, but I'll leave it to some of the experts. I'm just going to give a very quick brief overview of this, of how we then link the perception to then do actually strawberry picking potentially. But I want to move on to the journey also that it doesn't end there, right? If you guys have solved the manipulation problem, the big question is then where does it go? So you've picked this off the plant, but then we need to get it away from the actual crops, from the actual plants. And interesting from these sort of conversations we have with farmers and growers, you mustn't leave it out there for a very long time. At the moment, we've got human pickers picking these, they're very dexterous, they're very fast, but they pick it in trays, and those trays they kind of push along with them for a while. And the problem is indeed, if you don't get the crops after they've been picked into cool storage relatively quickly, they start deteriorating right there when they're on the fields. The just rule of thumb is that if you keep the fruits out an hour longer in the warmth of the summer, you lose about a day of shelf life of the actual product. So there is a strong ambition here to actually get these crops out from the fields into the cold storage as quickly as possible. So that's why we're exploring solutions for robotics logistics, where you will probably appreciate these farms can be quite vast. We're talking hundreds of meters of these polytunnels with crops on them. And already now, as I would say, I'm talking about this journey towards automation, we can think of solutions of how we can support some of the fruit pickers. So this is a solution that we can probably already deploy quite easily right now because the autonomy is already there and established through these other applications of UVC treatment, etc. It will also still persist and be around when you actually think about solving manipulation challenges. Because we're talking about what happens once you've picked it and how do you then quickly get it away. If you think about a scalable solution for the overall picking challenges, that is an area that is actually not so often looked at. And then of course the final bit is we're not talking about a single robot here, we're talking a fleet in order to cover 10 hectares, etc. So that's the sort of scale we're looking at. That is about 60 kilometers of these strawberry tunnels. And even if you are very good, you guys, on manipulation and actually being able to grasp these things very quickly, eventually we will need a scalable solution where we may have multiple arms on one mobile platform, but then these should be engaged really on the actual picking operation. And then the question is, how do they get the product off the field into some decent storage as quickly as possible? So there's a whole lot of interesting collaboration and integration there with telecommunication. We do some tests with 5G in order to facilitate really, really high bandwidth communication, also in order to exploit things like edge computing, so facilitating better deep learned models for the fruit detection and forecasting work, for instance, to not run on the individual robots, to make those robots themselves cheaper, so we can scale this up to larger scale fleets. I'm not going to talk too much about this. Just going to briefly talk about the picking one, because I think this is in the interest of this workshop. I'm just going to give you a gist of what some of the solutions look like. This is not the most recent version of our picking system that we are developing together with Saga Robotics. It's an older version, but it gives you a bit of an idea of what we're looking at. So you could imagine you may have parallel arms, several of those arms working independently, but of course mustn't collide with one another on a platform. And then you have this whole system moving along through a strawberry farm, really perceiving which ones are the right ones and only picking those. So you see a bit of a test bench at the bottom here as well that we've got in the lab, but we have our own little strawberry environment, farm environment in Lincoln that we are using to actually use. And you can probably appreciate that trajectory planning in these sort of clusters, when you're trying to reach something that's higher up, can pose an interesting manipulation challenge, really. So not spending too much on this, but you can get the idea. So we first localize those fruits. I've talked about a bit perception again. We've got our dedicated learned models to assess strawberries for ripeness, which also then feeds into some forecasting models so that we can anticipate how many strawberries will be ripe in a certain time in the future, typical horizon, something like 3 weeks. And in that context then we can schedule also when fruits should be picked, and we can then schedule these picking operations with this fleet of robots accordingly. And then it comes down to estimate exactly their 3D position here to then do the trajectory planning in these clusters of strawberries. This is the robot that we're using in a variety of these applications, and you see they come in different shapes and sizes, really, depending on the sort of application we're doing. So we've seen already some with its arch for UVC and spraying operations. What you see on the right hand side is one that is particularly designated for these logistics operations, so it can carry multiple trays of strawberries as they're being picked, and can move along. And it's all, we spend a lot of time to make these robots actually work autonomously, reliably on this larger scale in these environments. And indeed, this is the foundation for a lot of these applications. So when we think of here, you see in the top right, you see some operations at night where these robots are working on this commercial farm already, delivering this UVC treatment. And what underpins that is that we've worked a lot on bringing together laser-based navigation and GPS-based localization. And then we have, for all this, all underpinning is usually a topological map, so where we have the general layout of the farm, what are the main routes that these robots travel along. And then we may have also specific navigation modes. For instance, if we want to go in row these fields, we want to be very precise. It's a very narrow area to move in, so we have rather in the open spaces we have specific we've got general kind of path planning and what you would normally expect for robotic systems. Within the rows we deploy specific navigation that actually use the pole structures as they move along. And there's been a lot of work in order to tune these and make these reliable, so that by now these robots can autonomously cover those about 60 kilometers a week in this sort of an environment. And that one really is the underpinning foundation for a lot of what we're doing. So, and as I said, we're trying this on our little own farm, which is here on the left-hand side. That's our little experimental strawberry farm in Riceholme. That's only like 35 meters long. It's got 2 tunnels of 5 rows each. A quite scaled-down version. Here in the middle, you see the sort of more commercial size that we see. I think you can make out these different tunnels quite easy from here, and it's a challenging environment because indeed it's muddy, it's dirty, it's bumpy, it's overgrown. It's not quite as tidy as our nicely gravelled area up there, but that's the key bit, right? We need to get out into the wild and work for that. And that is also, if you think about the transition from doing manipulation in a lab space where you've got this all fixed and nicely calibrated and all tied down, the moment you go out into the fields and you have the entire platform moving and wiggling about, even though it may have suspension and everything, you are in a challenging terrain. And that is something that I think also, if you think about the grasp planning that you guys may be interested in, is an area you may want to consider. So how can we deal with actually vibrations, with bumpiness and so on? Where do you want to put your sensors in order then to be able to do this? And how do you actually do fast turn planning that can compensate for some of the dynamic changes that happen? You're moving into clusters of fruits that move out of the way. You are on a platform that isn't particularly sturdy, that's going to move. So you get an idea of the challenges that we may be interested in. Right, so I'm going to whip through this quite quickly here. We talked about logistics already briefly, and all you really need for logistics is a mobile platform that is reliable and can go from A to B. So that's something that robotics research has solved for quite a while, I would say, but it's still an interesting problem, and it still offers quite the potential for some productivity gains. Because indeed, even if we assume so far we're not going to solve the picking challenge right away, human pickers at this time in these environments, that can be quite long, spend around up to 20% of the time just transporting things, pushing things along, moving them from one place to another. And they may even be, leaving the crops out longer than ideally they should be, because it will have this impact on quality, as I said before. So if we are assuming we've got a mobile platform, that is robust and reliable and can move about from A to B. Now then the question, in order to serve people, becomes really a question of, well, where does this robot need to go? So where is our human picker? And which robot should I send there, and how do I avoid congestion in these very long areas that we've got in there? So that's some aspect that we may look at. And if you are looking forward, if you may have a fully automated system which also does the picking, you still have some of those challenges, because it's very unlikely that immediately we're going to go from all done by humans to all done by robots. So you want to still have a representation of where people are, even if it's just for safety purposes, to actually understand which direction they're traveling. So in that context, we had made some solutions and worked on some systems here that basically is a summon the robot device. So we assume something, people have these trolleys, you may have seen this before, where they push along while they are picking. We made some low-cost GPS IoT device that looks a bit like this as a prototype. We have got a newer version for that, and all it does really is it's got some very low-cost, bad quality GPS on it, and it's got 3 buttons where people can summon a robot when they need one. And our challenge is to send the robot to them, ideally anticipating when they need it, and to really also estimate very directly where this robot has to go. Because, as you've seen, this very long layout that we've got, it can be quite challenging to determine where a person is. So here you see one of these trolleys, you see a picker, and indeed these rows are about 1 meter apart, and you can also hopefully see that how narrow it can be for such a platform to go into. Now, normal standard cheap GPS does never give you the accuracy to go within 1 meter, but going into the wrong row, because you just had an offset of 1 meter of your estimation where someone is, it's going to be really costly. Because the moment you go in there, and as I said, they may be 3 meters long, you're traveling 300 meters in the wrong direction. So it's important that we actually estimate exactly where these people are. And what we are doing here is to exploit the topological structure of the farm. So what basically constrains the robots, because they only can travel down these lanes, and also humans only travel down these long lanes here. We can use that to integrate and actually exploit these topological constraints. We know they're not going to jump from one row to the other. They're going to be on their row, and they're going to keep working in that particular row. So we can really integrate a lot of the evidence from the different GNSS GPS readings here. And we can further augment this with some multimodal detectors that we have got, specific detectors on the robot platform itself, to then be able to complement the relatively noisy GPS readings that we get from these smart trolleys, as we call them, these devices. I'm not going to talk too much about this. It's a standard sort of topological map representation where we've got a set of nodes and edges, and we know that people can only travel along those edges, and these can be very long lanes that they can travel along. And if we have that, then we can actually implement a particle filter approach, so the Bayesian tracking approach, where we can track multiple hypotheses at a time. And what we actually do here is that we model the transitions from one node to the other as a continuous time process. So we use continuous time Markov models in this sense, where we have a certain expectation how long they are in a node before they traverse to the next one, and we have also a certain persistency, because people pick along the rows and travel in the same direction, and then eventually they will need a robot. So we can predict how full their trolley will already be and where they will likely be at some point in the future, exploiting that to schedule where the robots should be, and then not be surprised when they actually summon one and probably have one lingering nearby. So that's the general idea here. So we can use this for prediction, and then of course also for tracking, because we will get these these observations of where people are, and we can use this GPS to basically from this device, which gives noisy but identifiable information, so we know whose that is. And then we also have we can use the detections from a LiDAR system, which we can see here on the right hand side, which there we go, uses just the LiDAR information, and we can even augment this with further RFID readings if we want to. So it's a variety of sensors that we can integrate, and together they give us a very accurate estimation of where people are in this environment, allowing us to send the robot to the right places and also anticipating when they will need it. Now, I'm just going to be very quick about this. This indeed gives us enough precision and accuracy to then send the robots to the right idea. So here the green one is where it should be. This is the anticipated one. And we see if we wouldn't have this sort of constraints in it, then indeed the prediction of which row and which particular node it should go to is off quite a bit. Now, moving on. Once we know where to go, we of course also need to work which robot we're sending and how are we ensuring that we are not blocking each other in this system. Again, this is something that you will face in a fully automated system as well. So which robot should go picking where. If you assume that you've got another one that does the transportation, there's a bit of a handover between the picking platform and the logistics platform. You still have to solve this overall fleet challenge for a scalable solution of your autonomous harvesting fleets. And what we use a lot here is also to simulate and see the impact of deploying robots and what size of fleet and the particular topology we've got in there. We use a technology called discrete event simulations, which allows you to very quickly just model the transitions from one state to another. So for instance, a picker may currently be picking. After a certain time, the crate will be full. They move into the state of waiting for a robot. You want to keep that waiting state as short as possible. Then they will move into a loading state, and then it can go back to picking if they have an autonomous robotic solution that supports them. Now, these sort of discrete event simulations allow us to run through and analyze the actual productivity impact of our robotic solutions quite quickly. You just model the transitions from picking to handing over, etc. Based on some actual data that you've gathered in the farm environment, and then you can see what happens if I throw double the amount of robots in there. Will they start clogging up the system? Will they start hindering each other because there's only one ever allowed in one of those lanes? So that's a very powerful tool to actually do early on return of investment analysis, for instance. That gets the business people quite excited. And you cannot only do this for this sort of system that we're doing right now, where we have logistics supporting human fruit pickers. The moment you can actually quantify the performance of your autonomous picking system, you can throw those in there and see how quickly they will actually operate and be able to whiz through a farm environment. It's also the underpinnings, and then you can make an analysis of when you've got a break even, when does it pay off to throw robots onto the problem, and how many will you need to find a sweet spot in there. If you have several robots operating in such an environment, you also must make sure that they are not blocking each other. So we're doing what's called critical point analysis on these topologies. If a robot can basically reserve a certain segment to travel along, no other robot can go in there. And indeed, the topology that we've got is really determining how much of congestion you probably have to face, which probably gives you also an idea why this project overall is called Robot Highways. We're trying to optimize how a farm layout could be to gain the most out of a fleet of robots being deployed in there. Now, we're not going to go too much about this. There's a lot of interesting work on fleet coordination, the congestion and deadlock avoidance in there. There's one link here where we work with our colleagues in Oxford on these sort of problems. Okay, in the interest of time, I shall move on. There's also the challenges here that, of course, you may have. If you think about scaling up these, and you may have fleets of 20 robots, eventually you reach a point where they must be dynamically allocated to the fleet and also being taken out of service. For instance, they may have a mechanical failure, and you must be very, very dynamic in replacing them or actually solving the entire task still if there is one robot dropped out. So there's a lot of work in the task allocation overall to allow robots to be registered and unregistered dynamically and monitor their current status overall. Okay, cool. So I hope I gave you a bit of an idea of how the sort of fleet challenges and the scalability challenges, and that also if we come to an actual autonomous harvesting system, we will still have some of those challenges of moving about in a farm environment, in particular where it is so constrained and has got this sort of specific topology, and how we can already these days use robots to support fruit pickers here. Now I'm going to just very quickly show you a few slides on the perception challenge. You've seen some of those aspects already. We're not only trying to feed this into the harvesting itself, we're also trying to use this for forecasting into time series models, which are usually the type of LSTM deep learned models where you feed in the current perception systems and the features that you extract through some deep learned models and try to anticipate what the yield will be in the end. And this is on a paper here which is the underpinning a lot of our fruit perception work we're doing, so just going to whiz through this one. One big benefit, I would say, that robots also provide you with is that you can start doing autonomous data gathering. And now in particular when you want to learn for perception, for grasping, you will still need quite huge amounts of data. And what we have now set up, because we've got this very reliable autonomous system, is that twice a week these robots will go out autonomously and collect data. Very nicely registered data, because they can localize very reliably through the system that we've got. So we can do temporal data sets of seeing actually how crops develop from one, between 3 days, the change in there, so that you can actually do crop registration over time. And you see we've got 3 viewpoints in the system where we've got RGBD information, which we can then exploit to not only improve our perception systems, but also then to work towards manipulation, etc., because you can get an analysis of what sort of clusters do you have, where do they sit in 3D, and you can try to do trajectory planning within those clusters in there. That kind of gives you an idea of what we've got, and that indeed this system works quite reasonably well these days. And indeed the actual underpinning paper works not only just on strawberries, it can be trained on a variety of fruit, which gives you the exact 3D position then as you move forward. And through that we can count how many strawberries we've got, and we can feed this into time series models to overall get this information out there. Well, as I said, the key bit for us is also that we get the right data, and there's some work here on actually getting the data sets autonomously. As I've shown before, this is the sort of setup of our data gathering robots that already starts getting out again this season, right now on our experimental farm, and we get this very, very dense data sets, also temporally dense, where we can actually monitor the change of crops over time. Right, which is something I've already shown you. I'm going to quickly move through. We're not only doing this in strawberries, we also are exploring similar techniques in vineyards. So this is a European Horizon project called Bacchus, where we are also working to develop a harvesting platform and an inspection platform with a similar ambition as we've done currently in strawberries, to actually be able to monitor the crops, detect them, and then eventually cut those bunches of grapes and harvest them. Comes with its particular challenges, because these bunches are much heavier, much bigger, but in some way they're a bit nicer to be separated out. But there's really also a challenge to make sure that you don't damage any of the ones while you have some big, stronger manipulators and end effectors to go in there. Right, that shall be enough for now. I've given you a bit of an overview of our whole Raspberry program, where we have this fleet of autonomous robots that hopefully will transform the software production sector in a number of tasks. So moving really towards this integrated challenge of a fully automated farm, covering aspects from prediction of yield over crop care through UVC and spraying, all the way down to harvesting and supporting harvesting operations. So it's more a transition really. I would argue you still need a logistics solution even if you solve the manipulation challenge. There's a big perception challenge that is not just in order to be able to harvest, but also for this sort of yield prediction and assessment of the health status of your plants, and all doing this on a mobile platform comes with its extra also scientific challenges that go far beyond the sort of dataset driven research we're doing. Big challenge also for mobile manipulation in this context is to integrate the manipulation with locomotion. Of course, eventually if you want to be really fast, you want the platform itself moving along while you're doing the picking, rather than stop, pick, stop, pick. And with that platform and the sort of uneven terrain that you're facing, that's a really fascinating challenge. So moving forward to multi-arm solutions where you have not just 2 but maybe 6 robots operating in parallel and ensuring that their workspaces are nicely separated and there is no risk of any collisions in there, is a very interesting aspect in there. Alright, I shall end here. I hope I gave you a bit of the gist of what the challenges are in this domain, and there's something for you to take home from. Thank you.